Thank you very much for the introduction, and also let me take the opportunity and thank the organizers of this wonderful workshop for inviting me and allowing me to present some of our recent work that we did on light-matter interaction from first principles. And by this I mean that we want to use the most fundamental theory available to us to describe the interaction between charged quantized particles and quantized light field, and then make the resulting equation numerically tractable such that we get a unifying approach that we can apply to virtually all situations of low energy quantum physics. That is that we want a method that at the same time gives us nuclear, electronic and photonic properties of the combined light-matter system, and which makes such an approach specifically suitable to describe situations where matter and light degrees of freedom strongly interact and mix, and you get a change, presumably, of matter degrees or of properties of the matter subsystem, like in polaritonic chemistry, for instance, a change of chemical reaction allegedly, or that the properties of materials change due to addressing with the photon field. Now, the basic principle we follow is, not surprisingly, quantum electrodynamics, which tells us how charged particles and light interact, and it's actually pretty easy to understand from a classical perspective. From Maxwell's equation, we know that the charge current J couples linearly to a vector potential A, and we can make this into a quantum description by promoting the classical quantities to operator-valued quantities. That means we have a charge current operator. I will later show you how that looks like specifically in our case. And we have a vector potential operator, which is basically nothing else than a sum over all possible modes of the electromagnetic field. And for each mode, you can annihilate a photon in the mode K or create a photon in the mode K. And from this so-called minimal coupling prescription, we get this basic picture in our mind, how charged particle interacts. We have a moving charge, that means a charge current. And this charge current can eventually create a photon with momentum k, so the particle loses energy and momentum. The photon travels through space and can be reabsorbed by a different moving charge that then gains the lost energy and momentum. Now, we are not so much interested in the standard setting of QED, that means in the high energy regime where scattering description is most sensible. What we are interested in, and I think also most people in the audience, is the low energy regime of QED. Now, in this regime, it is sensible to make the following approximation, to think that the particles are relatively slow, such that we can treat them non-relativistically, and this allows us to discard particle creation, pair creation processes. So effectively, we discard the antiparticle degrees of freedom in QED, and this leads to a slight simplification of QED, which is called the Pauli-Firth Hamiltonian. I will show you later on how that looks like. Anyway, this is still then a full field theoretical description of the problem. So any wave function based method, or to solve the problem with a wave function, is out of the question, because we still have infinitely many degrees of freedom. So we would have a wave function which has entries that you have infinitely many coordinate dependencies, so to speak. So traditionally what then is done is to make an implicit choice. I prescribe how my photon field looks like, and then predict how my matter subsystem behaves, so the properties of the matter subsystem. Or B, I prescribe how my matter system behaves, and I predict what happens to the photon field. So let us see how choice A looks like. The standard choice is that we say, well, let's approximate the full photon field by the so-called lowest order longitudinal photon exchange, which goes as 1 over q squared. So the pictures are not so good on that display. But it's 1 over q squared, and if we transform this from Fourier into real space, well, it just gives us the Coulomb interaction. That means by prescribing how the field looks like, we get a particle-only description, and this is just the usual Schrödinger interacting many-body Schrödinger equation. That is the starting point of quantum chemistry or solid-state physics. Now let's do the opposite. Prescribe how the matter system looks like, and take as an example cavity QED. So we, for instance, take an atom, say a rubidium atom, and we know already in advance what are its properties. And then we say, let's put it into a cavity. And then we take a cavity that is such that a mode is enhanced that has a wavelength much larger than our matter system, that we already know it beforehand. And then we can do the following approximation, because we know for what the matter subsystem is concerned, it doesn't see really this dependence on, or the spatial dependence of the vector field. So we can just make it homogeneous, so not spatially dependent. We can integrate over the charge current. After a few transformation, we end up at this so-called dipole coupling term, where we have, instead of the charge current, the total dipole operator of the matter subsystem appearing. I will later comment on this. Anyhow, since we know already the properties of our matter system, and we keep usually one mode, then we know, well, actually it will only be those states that are relevant for our description that have transitions which are closer in resonance with this one mode, and we can discard all the rest. And that leads to the usual starting point of all the quantum optical models. You have a few modes and a few levels. Now, what we are interested in is in between. So situations where we cannot a priori treat either matter nor light as a perturbation of each other, but both degrees of freedom become equally important. And that's why we want to have an approach that can treat all of these problems at once. At that point, usually the question comes, well, but why do you want to do that? I mean, I can take a quantum optical model, it's well known, that I can reproduce, for instance, the Rabi splitting, or roughly how the spectrum changes where I put my cavity mode. So this is well described from quantum optics. Well, the point that I want to make here, that is seemingly true also to what everything we found, but it changes, I think, dramatically when we want to use the models to predict how the matter subsystem changes. That means if you look at other observables than the traditional quantum optical observables, these models are less reliable, and I want to give you two examples where they are really, really, really bad. Okay, the first example is a toy model that we can still treat numerically exactly. It's a gallium arsenide quantum ring. So this is the charge ground state density. The single particle sits in this Mexican head potential, and it's uncoupled. And then we couple it very, very weakly, really, really weakly, to a cavity mode that is polarized along this direction. So Jaynes-Cummings or whatever quantum optical model you use should well describe this. So let's see what, for instance, a few level approximation would give us. And we take here like the two photonic states, 3 electronic states, and then presumably we get a good approximation to the wave function. And a traditional observable that you can calculate then from this wave function is, for instance, this transition from the ground state to the first excited state that should slightly change. So it's basically your emerging lower polariton. But of course, since you have the wave function, you have a lot of other observables. And especially if we want to see how, say, chemistry or solid state physics is affected, the charge density is a very important quantity to look at. So what this model tells us, I mean, this is very weak coupling. So if you would look at this picture, you would not see a difference. So here we really only plot the difference between the bare and this coupled ground state. And what you will find qualitatively, you will get an enhancement or an accumulation of charge along the polarization direction. But of course, well, there are many other observables, like for instance, the mode occupations. And now compare this to the exact calculation. This is weak coupling, very weak coupling indeed. And what you find, well, this splitting, or this is the step to the lower polariton, is really well described. And you would also see that the Rabi splitting is well described. I don't display it, so because this we know by construction. But what the charge density is concerned, it's not even quantitatively wrong, it's qualitatively exactly the opposite. So what the model system or the model approximation would tell you is exactly the opposite of what in this model should happen. And also the photon occupations are not really good described. And now you would say, yeah, well, okay, take more states, then it will get better. Now let's look at one specific case, namely at the photon occupation, and increase the number of the electronic states. And then you see, yeah, well, the number seems to get closer to the thing that we know. But now you might think, well, maybe it's better, actually it's a photonic observable, we should put there more photonic states and not so much electronic states. Then it again gets worse. And this is seems to be a generic behavior that even in the weak coupling regime, that if you look at how the wave function converges to the full dressed problem, it's really badly behaved, and depending on the observable, it's really behaving wrong. And this gets completely problematic in the strong coupling, where it's a complete mess. Let's take a slightly more interesting or realistic case, and let's take the case of a 2D material. And the 2D material we consider is, I think, iron selenide or so, and it has a superconducting phase. And we can take this model and couple the phonon modes that lead to the superconductivity of the electrons to the cavity. And we don't only look at one cavity mode, but we take a continuum, okay? When we do that, and we couple weakly, really weakly, we see if we do the rotating wave approximation for the full coupled system of electron, nuclei, and photons, the spectrum that we get out is basically, or to a large extent, indistinguishable from the full coupled problem that we can still solve, okay? Now, you would say, well, this is well described, the splitting is there, fine, but then if you look at the thing that we're interested in, namely the how does the TC, so the critical temperature change, well, the rotating wave approximation tells you it will always enhance it, and the minimal coupling tells you it will always suppress it. So again, a situation where seemingly if you only look at the spectrum, everything is fine, but if you look actually really at the properties of the wave function, it's completely wrong. And that's why we think it's sensible to have a theory that really tries to treat the full system from scratch. And the theory we build upon is, as I said, QED, and we will use the so-called non-relativistic QED, which is the so-called Pauli-Fierz Hamiltonian. Let me walk you through this Hamiltonian. So you have Ne electrons, and you have the bare non-relativistic momentum of the electron. Then you shift the bare momentum by the total electromagnetic field that has two parts. You have the photon operators there, so these are really the photons that are created, and you have an external field, like this is, for instance, a perturbation that an experimentalist shoot onto your system, and this then shifts the whole thing to your canonical momentum. And then you have the Pauli or Stein-Geilach term that gives you your Siemens splitting. The same you do for the nuclei, but we do not really resolve, or we do not want to resolve the nuclear structure, so we don't take a bunch of protons and neutrons, but we just give it an effective mass, an effective charge, and an effective spin. And then the only thing I didn't tell you so far was what does this perpendicular sign mean here? And that means or indicates that we chose a specific gauge. And the gauge we chose is the Coulomb gauge. This is very convenient for us because it does one thing. It it distributes our field into two parts. We have a purely longitudinal part. Now the Coulomb interaction among the particles is not an approximation, because all the rest of the complexity is in the transversal part, and transversal means if you have a momentum of your photon k, then you have only two allowed perpendicular polarization directions, and that's the Coulomb gauge. And then you have the bare energy of your photon field. You can put there an integral. It doesn't change much. Now, two comments here. I talked about minimal coupling as J.A. This doesn't look like J.A. But this can be easily reconciled by just reordering the Hamiltonian slightly. We collect the bare kinetic terms of the particles and call them T. We collect all the longitudinal interaction among the particles and call them W, then the bare photon energy, and then indeed you find J.A, as you expect from Maxwell's equation, where the J operator looks a little bit complicated, but I just give it for completeness. It has three parts that are not so surprising. You have the paramagnetic current, you have a magnetization current because you have spin there, and you have the usual diamagnetic current. Now the second comment. Mathematicians have worked a lot on this Hamiltonian in the last 30 years or so, and they showed very, very nice properties. First of all, they showed it has a ground state, so matter is stable even if we put it in a continuum of photons. Secondly, they showed this Hamiltonian is self-adjoint. That means we can uniquely solve the corresponding Schrödinger equation. That's nice, but we will never be able to solve it because the wave function depends on infinitely many coordinates. So it seems useless. But what we then want to do now is to make this actually, or to rewrite it in such a way that we can solve it numerically, and we will rewrite it exactly, and we will rewrite it by actually using the physical quantities that appear in QED, and the physical quantities of QED are the charge current operator and the vector potential operator. And we do this by just using their equations of motions. The first equation we use is the time derivative of the charge current operator. Now remember, if you integrate over the charge current or get rid of the charge, it's just the probability current. If you integrate over the probability current, what you get out is the momentum of the total system or the meta subsystem. If you make a time derivative, this gives you a force. So what you see here is the quantum analog of Newton's force equation for electrons, nuclei coupled to photons. And the other equation that we use, not surprisingly, is just Maxwell's equation in operator form, and where the inhomogeneity is clearly the charge current of the meta subsystem. Now one needs to differentiate slightly between the static and the time-dependent case. I will now focus on the time-dependent case and only comment on the static case a little later. But for the time-dependent case, what these two equations allow me, they allow me to show the following. Given an initial state of the combined light-matter system that you determine, I can, in principle, this is what we can show, solve the corresponding Schrödinger type equation and generate all physically allowed wave functions. So not just any, but only physically allowed that I get from starting there. And if I do this and would write up all possible wave functions that are physically allowed from this initial state, I find a very convenient way to label them. Namely, I can label them just by their expectation value of the charge current operator and the vector potential operator. To put it differently, if you give me for a finite time in all of space J and A, I can uniquely, at least in principle, reconstruct the full wave function of the full field theoretical problem. That sounds like a funny mathematical oddity, but what is the consequence? And the consequence is very nice. If we look at the equations that we originally used to show this one-to-one relation, and now don't look at them as operator-valued equations, but actually look at the expectation values. So for the exact wave function is an exact relation. Now knowing that the wave function is in principle uniquely determined by J and A, I see suddenly these two equations are closed. So indeed what these two equations are, they are the exact quantum Navier-Stokes equation. And this seems like magic, because now we only have to solve these two fluid equations, and we can do this extremely efficiently on our computers. Well, there's always a catch, because there's always a conservation of misery. While the photon part is very trivial, it's just the Maxwell's equation, all the quantumness of the field, all the correlations, all the entanglement, everything resides in this pi term. And let me remind you what this pi term is. So it gives you the local forces. We can analyze them. Actually, we can write them down in terms of wave functions. And they have very, very nice physical, intuitive interpretation. They are momentum stress forces, interaction stress forces, compressibility forces, everything you expect from fluid dynamics. But we only know them in terms of the wave function. So we need to approximate this to make it practical. And this is hard. But we can follow Cohn and Sham that had faced actually a similar problem, but for the purely electronic case in the 60s. And they realized that it's sensible, instead of trying to directly approximate these force terms, just take an auxiliary system that is as close as possible to the original problem, but a fictitious one. It's not meant to be physical, but that shares as much as similarity as possible, and use the force terms that you get out from this to model that one. So effectively this means, it's the simplest case, we have many choices. The simplest case in our case is we just take a bunch of non-interacting electrons and non-interacting nuclei, and they evolve according with a mean field, so Hartree interaction, which is easy to solve, and an effective external field. This is not a physical system. I remind you, the only thing that this system should do, it should give you the right forces, and with the right forces, the exact charge current. So it's not the wave function that is important. This is the physical quantity that we actually after. And if we want to make the charge currents the same, that means the forces the same. The only way we can force this auxiliary system to behave or to show the same fluid dynamics is that we put the forces that are missing on our fluid that is moving through space at each point in space and time, and that leads to adopting the effective field to putting the forces back. And this is then the definition of infamous or famous Cohn-Sham type of, in this case, vector potential. And of course, this is still given only implicitly, but to approximate this stuff is much, much easier. And I will not go into detail how to do that. I will just show you what we have done in the end. We started with an infeasible problem that we can never solve in terms of wave functions because it's still field theoretical, and we turned it into a bunch of single particle equations, so for electrons and nuclei, but since they all see the same effective field, we just can propagate them independently. From these single particles, we can reconstruct the full fictitious wave function, which is then very easy. It gives us the total charge current. This we plug into a Maxwell's equation, then we have J and A, and we have to solve this self-consistently, and in principle we would find the exact results given we would know the effective fields. And as I said, I will not go into detail how to do this. There are several ways. But of course it's not easy. The nice thing about these equations is these we can solve highly efficiently on our computers. And I just give you one example. We can now do many other examples, but just the one that the movie I like the best is an acetylene molecule that we hit by a strong laser pulse, which is like 10 to the power 13 watts per square centimeter, 300 nanometers. And what will happen is it will just blow the stuff apart. So all the nuclei and the electrons just fly apart. So not so interesting. But the thing that I would like you to concentrate on the movie is how does the photon field, so the Maxwell field, change when I do that. No. Tab command.
Command tab. Or first command.
Okay, so the first thing you see that numerically is not so trivial because you have two simulation boxes. You have one for the light, because this travels at the speed of light, and you have a small simulation box for the actual molecules. And we make one strong simplification that for the 50 femtosecond time evolution that we calculate is not so important. We know this from molecular dynamics. We treat the nuclei classically. So, and then we just let the full thing evolve. And what is the difference is that in usual quantum mechanics, when you would solve this just with a usual quantum mechanics calculation, the field up there will never change because the charge currents that you induce will never talk back to the photons, so they cannot generate photons. And now you see, okay, it wobbles back and forth. You see here these arrows are the local field direction, so you see things happen, it blows apart, not so interesting physically, but when now the thing has passed, what you see here, the laser profile changes, and when the laser has passed, due to the fact that you really explode the thing, you have very strong currents, you still have a radiation going on there. And if you would do the same simulation with a slightly weaker or much weaker pulse, what you would see is you hit it, it wobbles, and then it stops wobbling because the simulation boxes that we use are open, so the radiation can leave. That means we have, from first principle, included dissipation and decoherence because, yeah, well, it's the environment we treat exactly, more or less. And we can, of course, look at other things that might be more interesting. This was just a test case for us. For instance, what we can do now is we can take two nanoparticles. They have like 297 sodium atoms each, and then we bring them close to each other, and then we can see if we perturb them slightly, how do the nuclei movement talk to the electrons, talk back to the photons, and we can see, we can switch them off and can see what are the influences to each other, what leads to enhancements of the local field in between. Now again, two comments. These simulations are really heavy in the sense of not only that you need a lot of numerical power, but also you need to develop completely new numerical ideas and solutions for problems that were not there before because we have a multi-scale problems of electron, nuclei, and photons. There's just no experience, so we, or in that case actually René, had to develop really from scratch a completely new numerical scheme. B, the second problem is we have no clear way to actually judge how accurate the simulations are because remember what we're looking at is the charge current locally and spatially resolved and the field, and we cannot compare to any other method. There are no analytical solutions except of trivial ones, and also to compare to experiments is pretty hard. So what we want to do to see how good our approximations are in practice, we make the problem slightly simpler, and we make it simpler by doing the longer wavelength approximation. You have seen that the boxes of simulation sizes are hugely different, 2,000 times. So it's really a good approximation. And in our case, again, this means we assume that the light field is, or the relevant modes, if you will, so we look at the low energy part more or less, so this should be captured pretty accurately, is basically homogeneous, and then you can integrate over the charge current. Then you do two transformation or three, and you end up with this R dot D. The R is, as said before, the total dipole moment, and the D looks on the first glance as if it would be just the mode resolved sum of the vector potential, but it's not. These things here, we call them Q, they are displacement coordinates, already indicate, they call displacement, and I call this D, this is the displacement field. And remember from macroscopic Maxwell's equation what the displacement field R is. It is the E field plus the polarization. So although it doesn't look like this, but we did something similar like this Polaron transformation needed to get there, these are mixed matter-light quantities, okay? It's not purely light. That's why it's not so surprising that if you do this long wavelength approximation for your full Hamiltonian of the Pauli-Fierz or the Pauli-Fierz Hamiltonian, you get this funny extra term that's sometimes called dipole self-energy or dipole self-interaction. It's basically something like this, but this has to appear physically because this is not the E field, this is the D field, and that takes care of that. And even if you might say, yeah, okay, I don't know what this means, mathematically, it's just a fact that if you do not include them, you can at least not talk about any static or equilibrium quantities, because without this term, the whole Hamiltonian has no ground state. Actually, it has no eigenstates whatsoever. So you really, at least mathematically, should keep it there. And this is what we do. And then we also take the dipole approximation for the external field that perturbs our system, is a classical one. And then something that we, in principle, always keep already on the full minimal coupling level, but just for simplicity, I didn't put there. I also have a term, a classical term, that perturbs my photon subsystem. So what is that? It's actually this mode-resolved external charge current, and what it does is it produces photons. So I can interpret this in two ways. It either just perturbs my photon system wiggles, so I generate photon and I see what happens with the rest. But effectively, in quantum field theory, people know this as source terms, and it's nothing else as I generate an initial pulse somewhere far away, so photons. So this is basically a classical perturbation to my matter-photon system, and this is the corresponding photon perturbation. And again, we could now compare the full time evolution, but that again is problematic. But we make it even simpler and only look at first order linear response. That means what we'll do is we start from the combined light matter ground state, and then we perturb this light matter ground state slightly, either with a classical pulse or with a quantum pulse, and then see what happens. And I want to compare to usual quantum mechanics and usual quantum optics in this regime. And the first thing that one realizes that knows quantum mechanics and linear response theory in quantum mechanics is that due to the fact that now we have the photon field there, so we do not prescribe how the photon field behaves. What you compare this is the usual quantum mechanical part. So this gives you, this is the density response function that you would see, because you fixed how your photon field looks like. You have no chance in quantum mechanics to adopt your photon field. But now you see, due to the fact that you have all the other coordinates, all the other photon parts there, you get a bunch of other response functions. And they are quite physical. And what is the implication of this response function for instance, a spectrum that we calculate? I will show you in a minute, but let's first focus on this funny response function, especially as this chi-m, chi-q, for instance. So these are photon-photon response functions. So it seems as if I perturb a photon, another photon reacts in another mode. And what at least you always hear is photons don't interact. But remember, particles also don't interact. It's actually the photons that makes them interact. And for the photon to interact, it's the particles that make them interacting. So what these are is, you see photon-photon interaction appearing. So to make it a little bit more specific, again in orange is what you would get from just standard quantum optics if you would not have matter there, okay? It's just free propagation. It would just follow the mode-resolved Maxwell's equation. So not much is going on. But now, due to the fact that we have the matter field there to induce interaction among them, we will get extra terms. And let's concentrate on these two extra terms. This is really now the merit when we go to this Coulomb type of description, because these ones, due to the Coulomb description, become explicit, and all the things that we don't know, here the approximations go in. But let's analyze what happens, because they give us already quite a rich physical structure what is going on. This one, so again, I put a photon in my system. So I put a photon and it hits my system. Due to the fact that I put a photon there, my matter polarizes. This is exactly what I expect, because we know from solid state physics you have polarization going on. This is this so to speak. This is an extension of the RPA, if you are familiar with the random phase approximation. So this gives you the polarization of the media. And this is a funny term because this shows you that the mode alpha prime talks to the mode alpha via an effective dipole-dipole interaction of the matter. So you basically, your mode reacts, you have a field, the field wiggles your particles around, of course the particles interact, generate in another mode a field, and this effectively leads to an interaction. And then the other terms are much more complicated. But here now comes the power why we actually like the long wavelength limit, because now we can compare to the quantum optical models that basically all work in this setting. Because we can now take, say, I don't know, the Ravi model, for instance. This is what we compared to. And I can do, okay, let's take the approximation that completely neglect this exchange correlation. So it's the simplest possible approximation I can do, neglect them, and see what happens. How good are we? And what we find is as long as we don't go to the ultra-strong coupling regime, it's actually pretty good. So that makes us confident that as long as we don't, without much effort, of course, for the strong coupling, we have to find better, we have to do approximations here. But that at least tells us that as long as we're in the weak to strong coupling regime or intermediate coupling, we should be fine. And a situation where it's really weak is actually free space. So we know the vacuum of free space really weakly interacts with my matter system, and then ignoring these extra terms, which are higher order complicated interaction terms, will not matter much. And indeed, what we do then, we can quite effectively solve this. We can take into account a few million modes. So, and we treat now the modes exactly in the same way like the quantum particles. So it's really a quantum description. And then what we find is, first, we reproduce what is known from the electronic structure community. We get the spectrum of benzene. So this is a real molecule. We do it from scratch. So it's not like that somebody tells us this is the peaks, these are the states. No, we get it from scratch. And there's one difference. So because you could say, well, I could calculate the energies before as well. But what you cannot get from quantum mechanics, because quantum mechanics has eigenstates that live forever. So you cannot get the line width. But due to the fact that we now effectively simulate the full bath, or at least we sample it with, in this case, 80,000 modes, so it's not perfect, at least. But what you immediately see is due to the sampling, you get from scratch the line width, so the radiative lifetime. And this is extremely cool, at least when I saw it the first time, because it allows us to do now the following. Now we can imagine we change the vacuum by, for instance, a cavity. That means certain modes are enhanced, others are suppressed. So we can now go there and actually really model how the modes change, and then do a self-consistent calculation and see what will happen. So what we did here is then, not with the full spectrum, but we basically artificially enhanced just the one mode that is in resonance with the lowest excitation of this benzene molecule. And when we crank up, in this case artificially, so basically we change the volume, if you will, of my cavity, we see the Ravi splitting appearing without any, except of basically my mode volume. This is my parameter. Of course, in these very strong regimes, we know it's not really faithful. So, but for the low ones, it should be fine. And well, then there's the other thing with the time-independent case. We can do the same for the time-independent case, but I think I will not have time. I don't know.
Still 10 minutes.
Still 10 minutes?
Yes.
Okay, then I can also explain this briefly, because it's a nice closing argument. You remember the initial problem that I showed you, these quantum rings coupled to this mode? And we can do this now with our approximations and see, do we capture the things that we want to capture? And indeed, if you look, again, I told you the density, if you look at the bare eye, you don't see the differences. But we capture the change in density and all the other quantities extremely accurately. Of course, the stronger we make the coupling, okay, this is a little bit advanced approximation called OEP, optimized effective potential, blah, blah. It's not so important. It's basically just, I take into account one photon processes. I can just increase it. I can take into account 2 photon processes. So we know that this approximation is good as long as the 1 photon processes dominate. And this is exactly what we see. If we increase the coupling at one point, it's no longer that good. Then we would have to put into account also by hand 2 photon processes. But that is good enough for us, because we can actually already go with this to quite strong coupling, and then we can look at real molecules. So the acetylene molecule that we blew apart before, we can now put into a cavity, and we can see how does the ground state change due to the cavity mode coupling. And of course, it's lamp shift physics, so the changes are really minuscule. You don't see it here, sadly enough, but it's really on the order of a few percentage, so not much. But what is more interesting than these changes, I mean, they will only become important in the really ultra-strong coupling, okay? And then we need to do a little bit more work to make this really faithful. Anywho, what is more interesting here is it gives us the access to completely new observable that mix matter and light. And what I show you here is this would be the reaction of your molecule in the cavity if I, from the outside, put a photon in the cavity. So these white dots go basically arrows inside, so it's a force map. The black ones go outside, and your molecule, if I put now a photon from the outside in, would make the shear motion. And you cannot do this with a classical light field, because a classical light field, if you look, at least if you take the dipole approximation, it can only do the following: it can shift everything in or shift everything out with the same amount. So this is a clear quantum behavior then. And well, with this, I think I come to my conclusion. So what we did over the last few years is we reformulated QED in a density functional or fluid dynamical way. And I say QED because we can do it also for the full QED setting. The problem there is the Dirac operator is known to have no ground state, so we cannot do eigenstates. So we can only do time propagation. That's why we like these Pauli-Fierz Hamiltonian a lot. We have a working implementation in Octopus. The photon things are not yet available in the official stream, but hopefully they get soon. And we have tested our approximation in the long wavelength limit, which we hope gives us enough understanding to see how accurate they are when we do the full minimal coupling calculations. And now, since we developed this machinery, to the good or the bad, I don't know, at least now we can actually really do applications, and people in our group now really working using this method to look at, okay, what happens with polaritonic chemistry, or what happens with materials when I really dress it strongly, either driven in time or with a vacuum field. And one thing that I'm personally more excited about, because I might get an understanding what is actually going on, what I didn't talk about is that when we put the photon modes back, we should actually not work with the physical mass, because remember, the physical mass of, for instance, the electron is the bare mass plus the electromagnetic mass. So in this, the electromagnetic mass, so what we call the physical mass, contains already the full bare vacuum. So we actually should need to work, and this is things that we analyze, with the bare mass. So what we suddenly see in quantum chemistry and solid state physics, we can look now, at least there is the possibility to look at the dependence of observables on the bare mass. And this is extremely cool. And of course, everybody that ever worked with DFT methods knows that they only go so far, especially in the strong coupling. We have to really put a lot of efforts in to make them accurate. So what we're also doing, we of course looking at alternatives that are well known in solid state and quantum chemistry. One thing that we did is, for instance, nobody forces you to use a non-interacting system as a reference system. What we do is actually we use a dressed system as a reference system. This is work we are doing. Then what is known from quantum chemistry methods, density matrices. You can reformulate also a fluid expression in terms of the density matrices. They can take correlation much better into account. And this is work that we're doing, and of course Green's function and blah, 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 you name it. And if you want to know more about like this alternative method of the density matrices, just go to the poster of Florian. If you want to learn why not only mathematically, but I think also physically this R-squared term needs to be there, then talk to Vasilis. If you want to see the terrible terms that I didn't show for the momentum stress tensor, at least parts of them, go to Marilena, she can show you. And if you want to understand more what we did with this response function and how we really sampled the vacuum, because we didn't sample the vacuum really faithfully, you have to talk to Davis. And with this I conclude, and thank you very much for your attention.